Okay, another example of a forpling situation, and we actually in the course have talked about methods that could be used to derive the fact that distance fallen is going to forple if the time of fall doubles. We haven't actually done that, but that is what we would get. Now, Galileo was the first to really sort of establish this. He didn't exactly state it this way: the distance of fall forples when the time of fall doubles. And they hadn't yet invented the word forpling, among other things. And of course, he was speaking in Italian, I believe, or writing. Okay, well, anyhow, we draw a forpling graph. Okay, again, this coordinate doubles, forples when this one doubles. And we say, okay, we're going to accept this. There are theoretical reasons why we suspect this might be true, and Galileo's experiments seem to support this idea. Okay, and of course we've established it with much greater precision than Galileo ever did, and it's extremely well verified. Okay, now let's say we do a not quite precise measurement and find that a 40-foot fall takes 1.5 seconds. Then the question is, how long does it take to fall 100 feet? Now, there's a way to use proportionality to solve this, and it's fairly straightforward, and we will probably talk about that in a second. But let's talk about the graphical method of relabeling, or of labeling. This graph is not yet labeled, of labeling this graph. Now, how would we want to label this graph to answer this question? Well, the first thing we would want to do is we would want to find some distance. We would want to have the 100-foot distance on our graph. So let's go ahead and put 100 feet and label now this distance fallen in feet. Make sure 100 feet isn't way up there through the ceiling or something. Okay? And then we want to put our 40-foot fall in the appropriate place. Well, if that's 100, then half of that's going to be about here. So 40 is going to be, I would say, maybe about here. And you can do that with greater precision. Let's see, 1, 2, and a half of those. This might be a little high. Now, to label the graph, of course, the reason we want to find our 40-foot fall is that we know that this takes 1.5 seconds, so that now we can label our x-axis. Here is 1.5 seconds. Okay? So now we just need to find what x-coordinate will correspond to 100 feet. Now we could break this 1.5 seconds down into 3 parts. So we have half-second intervals. Those don't seem to be very uniform, do they? Let's see, if I really use this interval, that would move this point over a little bit. Let's go ahead and do that. Okay, now 1, 2, 3. Yeah, that's pretty uniform. So we would have 2 seconds here and a similar interval out here to about 2.5 seconds. Now, if we come across here, come straight down here, then our honest estimate looks like it would be about 2.2 seconds. Between 2.1 and 2.2, we'll round it off to 2.2 seconds. And put a little question mark there because, again, this is just a ballpark. And not a ballpark estimate, it's a graphical estimate with whatever uncertainties follow from the way the graph is constructed, the accuracy with which it's constructed, and the accuracy with which we estimate these relative positions on the axes. Okay, now our proportionality. One way to express our proportionality is using the fact that this is a forpling graph, so that 2 to the p equals 4. In other words, this is y equals ax to the p, this graph, with 2 to the p equals 4, so this is y equals ax squared, where a is a proportionality constant. And we're not going to actually evaluate a right now. We're going to just do this by the fact then that if y2 corresponds to x2, y1 corresponds to x1, then y2 over y1 is x2 over x1 quantity squared, and this is very easily established just by the algebra. Okay, now y2 and y1 are our two distances, so let's let y2 be the, well, we know the two distances. Okay, let's let x2 be the unknown time, so that x2, and I'm going to call that t for time, over x1, which is the 1.5 seconds. Okay, this is a time to fall 100 feet. This is 1.5 seconds. That would be like our x2 and our x1. And then the 1.5 seconds corresponds to y1. 1.5 seconds corresponds to 40 feet. And then y2 would be the 100-foot distance, the distance that corresponds to the x2 time of fall for 100 feet. And of course, this side is squared. So we solve for t. And I'm not going to do that solution. You should be able to do that solution. If you can't, let me know. Let me know what you're trying to do to solve it, and I'll walk you through it. I'll point it out here. We just square this side. We get t squared over 2.25 seconds squared, and that's multiplied by the 2.25. That's multiplied by the 100 feet over 40 feet, which is 2.5. 2.5 multiplied by 2.25 is approximately 6. So the t is going to be approximately the square root of 6, which is 2.2. So we get t is approximately 2.2 seconds. Now you can do a more accurate solution. You could get this down to several decimal places, but remember that our 40-foot fall was not quite a precise measurement. Okay, if we time that with a stopwatch, it's hard to time something as short as 1.5 seconds with a whole lot of precision unless you're very, very well practiced. If you time it by counting 1001, 1002, you're even less precise. So don't know how this was timed. If it was timed using precise electronic methods, we might be able to determine at the time of fall from 100 feet to greater accuracy than just the 2.2 seconds. We might be able to justify additional significant figures. But with a not quite precise measurement, 2 significant figures is probably about as well as we're going to be able to do this. And I believe this solution probably ends up correct, 2.2 to 2 significant figures. Okay, I made a bonehead mistake there. 1.5 squared is 2.25. This is 2.5. If I take the square root of the product of 2.25 and 2.5, the result is going to be more than 2.25 and less than 2.5. And it's actually going to be pretty close to halfway between. And halfway between is going to be closer to 2.4 than it is to 2.3, between 2.3 and 2.4, but closer to 2.4. So my 2.2 was a off-the-cuff, quick calculation while I was trying to explain something, and I just made a bonehead error. You should be able to do that mentally better than I can. Okay, you're younger, your minds are more flexible. However, you don't have the experience with making these estimates. You should get that experience. You should be able to make those estimates without reaching for your calculator. that sort of thing in this sort of context significantly enhances your number sense, which enhances your ability to think about and visualize things without having to resort to machinery and just to believe the results of the machinery. It's important to be able to use the machinery and to confirm and debug your results also. But part of that process is being able to understand the numbers and how they relate. Without going into, you don't have to be able to calculate pi in your head to 10 decimal places. You don't even have to have it memorized to 10 decimal places. 4 is plenty for most applications. But some sort of number sense, some sort of ability to do a little bit of mental arithmetic instead of reaching for the calculator every time you need to do a calculation can be very beneficial.